This video is the first one in part of a series simply on epsilon-delta proofs. If you're walking in from high school into university, into higher level programs, you may face this whole concept and be asked to show through epsilon deltas that a limit exists. So this video is only going to be about explaining the definition itself. And then the future videos are going to have full out examples from linear, quadratic, and so on, where I am taking the various different examples and then showing step by step how to find your deltas for a given epsilon. So let's break down this definition. Some of this will be familiar to you, and then the epsilon delta itself probably will not. All right, so the first step is, it says that let f of x be a function defined on an open interval around a, except possibly at a itself. So what does this mean? Well, so if you take your standard axes, okay, so let's say this is your x-axis. Your x-axis would be your input into your function, and then we typically label this as y. Now y is actually f of x, so that is the function itself. So what is happening is this. You can imagine that you have your function f of x, and what you're trying to do is you have an input into this like any other function. So that would have been x, and it spits out for you values that then you can graph. So for a corresponding x, you can get a corresponding y. Now what this is saying is that you're going to assume that for an open interval, so not a closed interval, so it doesn't actually close in the values themselves, that you have an open interval. So open intervals like this, right? So we do it in round brackets. So around some value, now that particular value is going to be a. Now this does not necessarily mean that it includes a. All right, so I'll put an open dot in here, and this is a. So we do not need for this to be defined, meaning the function, if you substitute a into the function, doesn't have to necessarily be defined. But what has to be defined, okay, is an open region around this a. So for all the values except maybe a, and then except maybe the intervals around there, you need x to be defined at that function. That's the first part, right? So that's what this says. This and all the way through here. So now that we have some region that this function is defined, then we can talk about a limit. This is not new to you if you are actually taking a course that deals with epsilon deltas, because it means you have taken calculus and probably advanced functions or something like that. So this isn't new to you. So what this is saying is that the limit of x as it approaches a, okay, is equal to L. And what we want to do now, which is a little bit different than what you have done in high school, is we want to be able to understand what in the world does all of this mean right here. What do we mean that the limit exists if, okay, we have for every epsilon greater than 0, there exists a delta which is greater than 0, such that for all of the x, now this means all of the x within here that are defined, then this holds true. And when I say this, okay, I'll try to explain it visually for us. All right, so let's take a look now simply at this expression right here and break down what exactly are we trying to do here. So the first one, which is for every epsilon greater than 0. Now notice the epsilon greater than 0 appears, okay, so that epsilon appears right here. And this is what we are saying. So as you can see here, so if we have our x, okay, we have our f of x. Notice that we have our a somewhere within here. All right, so that's going to be x approaching a. Well, the epsilon, when we say for every epsilon greater than 0, What that gives us is it gives us bounds. So it gives us bounds around the limit that we are looking for. So wherever that limit is, okay, so it's going to be, okay, as we are trying to find it, these values, okay, so as you go up, okay, around here, that is epsilon, all right, and this is epsilon. So it is bounded within here by epsilon, right? So right here and right here. Now epsilon can be made as large or as small as possible. Now because we're talking about the limit, then typically we want this, smaller and smaller and smaller, as you can imagine. So we get closer and closer to L. So this would be shrinking, okay, as we're going in here. Now, what the epsilon delta states is, you pick this. So let's say someone picks this. It can be as small as they like. All right, so that's the first step. Okay, so you've picked your epsilon. Now, what it says is, now if you have an epsilon, you have to now find a delta. A delta such that for all of x, all right, so now what do we mean by a delta? We mean this. Delta now is going to be bounding your x. So notice that I have now added up a bound on the x, and it is around the value that I want x to approach in, and it is going to be a minus a delta and a plus delta. So these now bounds right here, that is your delta right there. So if someone gives you an epsilon right here, so if we have an epsilon, which bounds our limits, now we want to be able to find a delta for that given epsilon. Any value of x that is going to be bound within this right here. So this statement right here, from 0 greater than, so notice x minus a around delta. So that's where we are bounding our x. So notice this is exactly what we have here. So when we write this statement, what we are saying is you can now pick any x inside of here. Now, notice that it's less than, there's no equals, so you're not picking at these points, at this point, or at this point. You're not picking here, but you can pick any x you like anywhere else within that bound. And when you pick any x, doesn't matter which one, then what you will have, so this implies right here, so if you're going to be stuck in there, then you automatically will be within an epsilon of your limit, because you're going to be substituting any x from here right there. So you can evaluate what this value is, you can subtract it from the limit, and now you have to see if that is the absolute value of it is less than epsilon. All right, so that's what we want to be able to do. So visually, so we have something like this. So imagine this right here, all right, on some smaller interval, so from here to here, okay, on the x right there. So that is your plotted f of x. That's your plotted f of x. And now someone comes along and wants to tell you, okay, here is your epsilon. So now you've bounded right here. Can you now find a delta so that any x that you choose in this interval right here is going to give you a value that is bounded within that epsilon from top to bottom. All right, that's what the definition states. Let's take a look at several examples so that you can see this, and hopefully it will start making more sense to you. So here is the first example, okay, that I have. So let's imagine now So the blue right here is some portion of the function that is plotted. And someone has come along and has given you an epsilon. So they've given you an epsilon so that it bounds within here, all right, as you're going through, and is asking you, can you now find a delta? Now here, does the given delta satisfy the condition of the epsilon delta proof itself? So now, if they have given us a delta such that, so notice now we have picked a delta within here, so some value of it, and it now bounds, okay, so from here to here. And if we now, so A is somewhere in the middle in there, so if we now take any value of x and we substitute it into our function, so we're going to get these values right here. And now the question is, are those values bounded by the epsilon that has been given? So in here, notice if you go all the way, so this will cut it off right here, and it will cut it off right here. So notice any value of x that you choose, it's going to give you values that are of that nature. So that would be lying somewhere within here. And if you're lying somewhere within here, so now the question is, are you within the epsilon? And the answer is yes. So within here, we are within epsilon. Now, if we made this, okay, smaller, so that narrowing would get closer and closer, then we would definitely still be within the epsilon, because what we would be doing is we would be drawing these out, and this would become smaller, and therefore we're still in this bound, which is bounding this by the epsilon which has been given to us. If we made the delta bigger, we can certainly make it bigger, but there is going to be a maximum. So notice if we kept moving this eventually, so right here, and it looks like right here, so at those 2 points, let me mark them down. So at right here and right here. So we can certainly make the delta bigger and we would still be within the bounds of the epsilon. But if you moved this beyond this point, such that, for instance, you know, your delta that you would have would be like this, and then therefore this would be something like that. So now, well, this delta would not work for the given value of the epsilon that has been given. Why? Because if we would choose values that would be right here, for instance, or all the way right here, then you notice that the f of x would have been above the cutoff of the epsilon. So there is a maximum delta. So it looks like this would have been our maximum delta that we could have chosen. And anything smaller than that would always be bounding this within the range that is shown. So that's example 1. Now in this example, this chosen delta has worked. Here's example 2, where it also works. Now notice this looks like it's just a constant. It looks like it's just fixed. So whatever f of x is on this little interval right here, from here to here, so it looks like it's just stuck basically at L. So now the question is, all right, so for this given delta, which cuts it off over here, any value of x that you choose, so any value of x that you choose here is going to always give you this value back, which of course is bounded by the epsilon that has been given. So this delta also works. Now it turns out, I mean, we don't know, at least up to this point, from here to here, we certainly could have made the delta bigger and it would have still worked. Now we don't know what happens beyond that, so we would be bounded within there, but that delta would work. So anything smaller, okay, would work within here. Now anything bigger we don't know because we don't know what's happening to the function. So for this given epsilon, the chosen delta works. Here's an example right there, which is your third example right here. So let's see, okay, with this bounds, okay, that does it work or does it not work? Okay, so again, so they have given us, so here's the limit. Okay, here is going to be bounded by the epsilons. So this is L plus A, L minus A. So we have it. So we're bound within here. Now, for this given delta, right, so does this delta satisfy the epsilon? And again, notice that would mean, so if you're cutting this off, are you within these boundaries? And the answer is yes. Any x you choose inside of there is going to give you an f of x, which is bounded by the epsilon. So that's what we're looking for. And of course, the idea with this is to make epsilon smaller and smaller and smaller. You can choose any value, and it will just be adjusting the deltas. Now, here is an example where it doesn't work. So for instance, again, so here is your epsilon. So between here and here. So this is L plus epsilon. This is L minus epsilon. So it bounds right there. Okay, so it looks like A is somewhere over here. So this would have been a value right there. And now we have chosen a delta. Now that delta is going to be bounding over here and bounding over here. And now the question is, does this delta work? And the answer is no, it doesn't work. So why doesn't it work? Because I can pick an x. For instance, I can pick an x right here. And notice that x will have a value that's going to be right here. And it is now above, right? So it is beyond the cutoff of the epsilon that is allowed. So this delta will not work. Now this also happens over here on the other side. It also doesn't work there. So that delta is too big. So we need to now find, okay, is there a corresponding delta that will work? Yes, there would be a corresponding delta that would work. In fact, we can take this and notice what you can do is if this is your A, what you typically will do is you're going to find the maximum values within here. And those maximum values, it looks like they would be right there. And you can now go down all the way. Right, so if this is your A, right there, now this value of delta, so this new value of delta, would now work because it's going to now bound our f of x within the limits. And of course, anything smaller than that would also work. And anything bigger than that actually does not work. And we've just seen the example right here. So that's one example where it does not work. Here's another example. Now by this one, again, for the given epsilon that we have, which bounds this within this range right there. Now your A, okay, so it looks like it's somewhere here. Now notice your delta bounds it within here, so it goes from here to here. And for this, does this delta work? Yes, it does. Because again, any value you pick for x right there is going to give you a value for f of x that is bounded within the epsilon around your limit. So this one works. And again, now someone can ask you, what is the largest delta? Well, then you can just keep going. And it looks like the largest delta is going to be somewhere between here and notice here. So you can actually make the delta much bigger. This was a conservative delta that was chosen. And for that delta, notice that all of these values, of course, if you choose values within here, right, you can still get and be within the bounds. Now, it can't be any bigger than that because, at least up to this point, notice that now you're crossing over and you're beyond the allowed epsilon. So this delta works, and we can certainly find a bigger one, which is going to be in your epsilon delta proofs. The delta you're looking for is typically going to be what's the maximum delta that you have, or at least can you find as close to the maximum. Here's another example. Does it work over here? So the question, hopefully now you can see it. okay, pretty quickly. All right, so you're given an epsilon, okay, so it bounds right there, right? And here, the chosen delta does not work. It's too big. Because if I pick a value which is right here, notice it's going to get me outside of the bounds within the epsilon. And this one right here also gets me outside. So again, the question now arises, can you find, does delta exist? Well, yes, we can make delta smaller so that it just crosses. So it would have been right here. So that would have been, let's say if this is your A, so it's a much smaller delta, but this one would have worked. The one which has been chosen does not work. And now, of course, you might be interested in, okay, so how in the world can I find these deltas? Because it appears that these deltas are dependent on the epsilon that's given. And that's correct. That's why it says for every epsilon, there exists. So you give me an epsilon, can I find a delta that will work? And typically what we want to do is we want to find a delta, okay, relative to an epsilon. So it's going to be almost like another function, okay, delta dependent on epsilon, right, that you have. And here's a nice little illustration in terms of visuals. So here, now that you can see, here's your epsilons, okay, and deltas. So this is the one which is the largest one that could be found for this function. Notice, and I can make this, larger, and it adjusts my delta, okay, and here it makes it smaller, and it adjusts the delta. So the delta will get smaller dependent on the epsilon, right, that you have. So there you have it. All right, thanks for watching. Hopefully we'll see you in part 2 of the series, where I'm going to go over linear epsilon delta proofs and how to go about them.